Just as group homomorphisms were essential to our understanding of groups and comparing one group to another, ring homomorphisms are going to be essential to our understanding of rings. Now, the definition of a ring homomorphism will be very familiar. It's just the ring analog of the group homomorphism definition that we used before, and in fact, many of the theorems and facts about ring homomorphisms are going to be analogous to those of group homomorphisms. So let's start with the definition. Definition 106. Let's let R and S be rings. A function phi from R to S is a ring homomorphism if for every x and y in R, we have that phi of x plus y is equal to phi of x plus phi of y, and phi of x times y is equal to phi of x times phi of y. These two conditions are sometimes referred to as the function phi respecting addition and multiplication. So it respects the operations on the rings R and S. Also note that the operations occur in different places. So for instance, the sum inside the function occurs in R, so that's the addition on R, whereas the sum on the outside here is between elements of S, so that's the S addition. Occasionally we will run into situations where the rings involved will have very different operations that they call addition or that they call multiplication, and so it's important to keep track of where the elements are living that are being added or multiplied together. Now, continuing this definition, we have that if phi is a bijective homomorphism, ring homomorphism, then phi is called a ring isomorphism. Iso is the Greek word for same, morph as the word for shape or form. And we call phi a ring isomorphism because when there exists such a function between two rings, they are considered basically the same algebraically. If R and S are rings, and there exists a ring isomorphism phi from R to S, then we say that R and S are isomorphic, and we write that R is isomorphic to S. So we talked about groups being isomorphic to one another. Now we're talking about rings being isomorphic to each other. Now, what isomorphism means for algebra, for rings, is that two isomorphic rings are basically indistinguishable from an algebraic perspective. The only things that are different about them are the ways that their elements are labeled. An isomorphism phi that goes from R to S, it's bijective, so it's 1-to-1 and it's onto, which tells you that there's a bijective matching up of elements. Furthermore, the fact that it's a homomorphism means that the operations that happen in R are basically the same as the operations that happen in S. And so we typically will refer to rings in terms of what they're isomorphic to. And most of the time we won't distinguish between two rings that are isomorphic, and a lot of what we do in algebra is taking advantage of isomorphisms or proving isomorphisms between various algebraic structures, and knowing that two things are isomorphic lets you translate information back and forth between them. So let's look at a few examples of isomorphisms and homomorphisms. The most basic example, but one that's important for establishing a fact later on, is that we could take the identity function. The identity function from R to R, which just takes an element to itself, is always an isomorphism. This shows that any ring is isomorphic to itself, which it really ought to be if isomorphism has the qualities that we want it to. For another example, let's look at the function phi, which we're going to define going from the complex numbers to the complex numbers, given by phi of a plus bi is a minus bi. This is the conjugate operation. It takes a complex number to its conjugate. We claim that phi is a ring homomorphism. In order to prove that, we need to show that it respects both addition and multiplication. So the easiest or most straightforward way to do that, I should say, is to take two arbitrary elements inside your inside the domain of your function, and then we want to prove that phi of a plus bi plus c plus di is equal to what we get when we do the operations outside. So here we're adding things inside the domain before we apply the function. Here we're adding them after we apply the function. In order for phi to be a homomorphism, these two must work out to be the same, and similarly for multiplication. Now in this case, it's something that we can work out pretty quickly. So if we add these two complex numbers inside, we get a plus c plus b plus d, which gives us a plus c minus b plus di. That's just what phi does. It gives us the conjugate. Now we're going to apply phi first and say that this is a minus bi plus c minus di, which, if we gather things up, gives us a plus c. Then minus b minus d is the same as minus b plus d times I. So they're equal. So this handles addition, showing that it doesn't matter whether you add before or after. We do a similar thing with multiplication. So here, if we multiply first, then we've got to take advantage of the fact that I squared is -1. So we get AC minus BD plus AD plus BC times I. And so if we multiply first and then apply phi, we get AC minus BD minus AD plus BC times I. And then if we do it the other way around, if we take phi of the two complex numbers and then multiply them together, we'll get that we have a minus bi times c minus di, and multiplying all this out, we'll get ac minus negative b minus d plus, and then a times negative d plus negative b times c times I, and then you can look at this to note that they are in fact equal to one another. So that shows that phi respects addition, respects multiplication, and therefore phi is a homomorphism, a ring homomorphism. Furthermore, it's pretty easy to see that phi is bijective. The easiest way to see that is just to show that it has an inverse. In this case, it is, in fact, its own inverse. Now note that for any a plus bi that lies in the complex numbers, if I take phi of a plus bi, if I compose phi with itself, that gives me phi of a minus bi, and phi of a minus bi is a plus bi. So that means that phi is equal to its own inverse. So, in fact, phi is bijective. And since it's a bijective homomorphism, phi is an isomorphism. Now, this shows that the complex numbers are isomorphic to themselves. We already knew that, actually, because we always have the identity isomorphism, but here we have an example where we've got another one. Phi is not the identity function, but it is still an isomorphism from the ring C back to itself. Let's look at something that's not an isomorphism, or not always an isomorphism. Let's let n be any integer, and then let's let phi be the function from the ring Z to the ring Z mod nz be given by phi of x equals x bar. And by x bar, of course, we mean the coset of the ideal nz with representative x. Now, in this case, phi is a bijection, not a bijection, a homomorphism, basically by definition. Because if I have phi of x plus y, that's by definition x plus y bar, which is x bar plus y bar, because that's just how we define addition inside the factor ring, which is phi of x plus phi of y. And similarly for multiplication. This phi here, by the way, going from a ring to a factor ring of that original ring, is an example of a projection map, the natural projection map. We'll look at, we'll see this a couple more times in a little bit. Now, phi is certainly surjective, since given any x bar in Z mod nz, we have that x bar is equal to phi of x. So phi is certainly surjective. However, if n is not equal to 0, then phi is not injective, since phi of 0 is 0 bar, but that's the same as n bar, which is phi of n. And so we have two different inputs to the function giving the same output. So this shows that phi is not injective, and so it's a homomorphism, it's a surjective homomorphism, but it's not injective. And if n is not equal to 0. So in particular, phi is not a bijection. However, that by itself doesn't by itself mean that the two rings Z and Z mod nz are not isomorphic. Because to say that two rings are isomorphic simply means that there exists some isomorphism between them. Building a particular function and showing that it's not an isomorphism isn't enough to show that the two rings aren't isomorphic. So proving that two rings are not isomorphic sounds like it could be difficult, because you have to consider all possible homomorphisms between them. In practice, it's often not too difficult to prove that two rings are not isomorphic, because essentially and intuitively speaking, isomorphic rings have all of the same algebraic properties. Anything that you could describe about a ring using algebra will be exactly the same, whether you're looking at a ring or another ring that's isomorphic to it. So, in particular, if n is not equal to 0, then Z has infinitely many elements, and Z mod NZ has finitely many elements. Therefore, they can't be isomorphic to each other. There are lots and lots of other ways that we could look at this. We could say, we could go back and talk about the characteristic. We could say that the characteristic of the integers is 0, whereas the characteristic of Z mod NZ is n. We looked at that before. And the characteristic is an algebraic object that has to be the same if you look at two isomorphic rings. All right, for some non-examples, there are lots of functions that are very nice that we've dealt with before, and that maybe are even group homomorphisms, but that fail to be ring homomorphisms. So the following functions are not homomorphisms, are not ring homomorphisms. So for example, the function f from z to z given by f of x is equal to 3 times x. Now this function actually is a group homomorphism where we're looking at the additive group z, but it's not a ring homomorphism because it doesn't respect multiplication. So to show that something is not a homomorphism, you just have to show that it fails to respect addition or it fails to respect multiplication. So for instance, we have that f of 4 would be 12, but f of 2 times f of 2 would be 6 times 6, which is 36, which means that f of 4 does not equal f of 2 times f of 2, even though 4 is equal to 2 times 2. So f does not respect multiplication, therefore it's not a ring homomorphism. All right, well, how about f from z to z? Let's have that given by f of x equals x squared. This function does respect multiplication, because if I have f of x times y, that's x times y squared, which is x squared times y squared, which is f of x times f of y. So this function respects multiplication, but it doesn't respect addition. F of 3, for instance, is equal to 9, but f of 1 plus f of 2 is equal to 1 plus 4, which is 5. So we have that f of 1 plus 2 does not equal f of 1 plus f of 2, which means that f is not a ring homomorphism. It does not respect addition. And then if we take the function f from z to z, given by f of x equals x plus 1, well, this doesn't respect either multiplication or addition. If you wish to prove that a particular function is not a ring homomorphism, as long as you can identify whether it fails to respect addition or multiplication, then it will typically fail it all the time. It will typically fail to be a homomorphism nearly all the time. So if you just take random elements of your ring and put them into your function and compare like f of a times b compared to f of a times f of b for random values of a and b, then you will usually stumble upon a counterexample very quickly. It's difficult for a function to be a homomorphism most of the time, but not all the time. So if something's not a homomorphism, it typically fails in nearly every place that it can. All right, so let's get to some definitions and theorems regarding ring homomorphisms. Many of these statements are going to be very similar to statements that we had for groups, and so we're not going to spend a lot of time proving these, except maybe in some exercises. So first we need definition 107. This is going to look very similar to definitions that we had for groups. So let's let phi from R to S be a ring homomorphism. And let's let 0 subscript R and 0 subscript S be the additive identities. That is the zeros of R and S, respectively. So we've got 4 terms we're going to define. If A is some subset of R, then phi of A is by definition the set of all images of elements from A is called the image of A under phi. So it's a set of all things that you get when you plug elements from the set A into the function phi. If B is a subset of S, then phi inverse of B is, by definition, the set of all things in R, the set of all x's in R, such that phi of x lies in B, is called the preimage of B under phi. The kernel of phi is the set kernel of phi, which is the set of all elements in R such that phi of x is equal to the 0 element in S. So we could rewrite this also as the preimage of the 0 set in S. So the kernel of phi is the set of all things in R that get sent to 0 under the homomorphism. And finally, the image of phi is the set im phi, which is phi of R. So it's just the set of all things in S that you get from some element of R by plugging it into phi. All right, so all of these definitions are nearly exactly the same as the ones that we had for groups. In fact, they are exactly the same if we think of R and S as simply being groups under addition, and phi as being a group homomorphism, which of course it is because it has to respect addition. All right, so now we're going to get a theorem. There's going to be lots of parts to this theorem, and it's establishing basic facts. They're important for us to know, and we'll be using them a bunch, but we won't always make explicit reference to what they are. So I'm going to write them down and sort of talk through them as we go. And we're not going to do a proof of any of them. Most of them have very, very quick proofs. Very simple ones that are just like the ones for groups, and so we can look back there for most of the details. So theorem 108. Let's let R and S be rings. Phi from R to S, a homomorphism. Let's let A be a subset of R, B a subset of S. Let's let 0R and 0S be the additive identities of R and S, respectively. and then the following hold. All right, so part one, the image of the zero element is always the zero element. We're always guaranteed that any homomorphism takes the additive identity to the additive identity. For any x in R and n in Z, phi of nx is equal to n times phi of x. Remember that when we write an integer times a ring element, we mean the n-fold sum of this. This means add up x n times, or if n is negative, it means add up negative x negative n times. So we can take integer multiples and move them outside. For any x in R and n in the natural numbers, phi of x to the n, the power of x, is equal to phi of x to the n. So we can also move exponents from the inside to the outside of homomorphisms. Notice that we have to say that n is in the natural numbers because we don't necessarily know that we can raise arbitrary ring elements to negative powers, because most ring elements, or many ring elements, may not have inverses if you're not a field. All right, 4. If A is a, now we said it was a subset, but if it has a little more structure, if A is a subring of R, then phi of A is a subring of S. Number 5, if B is a subring of S, then phi inverse B, or the preimage of B rather, the preimage of B is a subring of R. Furthermore, if we know more about B, if B is an ideal of S, then phi inverse B is an ideal of R. This is showing that certain properties of the sets A and B are carried through when you go forward and back. So if you've got a subring on one side, then either its image or its preimage is going to be a subring. Now, if B is an ideal, then the preimage of B is going to be an ideal of R. But unfortunately, the same is not true going the other direction. If A is an ideal of R, then phi of A does not necessarily need to be an ideal of S. Now, we're going to have another condition in a second. It turns out that that will sometimes be the case, but not in general. So, especially when you're first working with these concepts, make sure that you're checking back, because there are some differences between looking at the image of things and looking at the preimage of things. In many ways, in many cases, preimages work sort of nicer than images, in that more things are preserved. In fact, we can go further. It turns out that if B is a prime ideal of S, then phi inverse of B is going to be a prime ideal of R, unless it's the whole ring itself. Let's continue on. Number 7. This one is really important. We're going to use all the time. Phi is injective if and only if the kernel of phi is equal to the zero ideal, which is just the set containing 0. I should specify that this is 0 inside R. This statement here it's actually exactly the same statement as for rings, that a homomorphism is injective if and only if the kernel is trivial. Now, part 1 guarantees that the zero element of R will always be in the kernel of any homomorphism, and if that's the only thing in the kernel, then phi itself is injective. Number 8 has to do with composing homomorphisms. So we already have phi from R to S. So if psi from S to T is a ring homomorphism, then the composition psi composed with phi, which is a function that goes from R to T, is a ring homomorphism. So the composition of homomorphisms is a homomorphism. Now, we've got some more statements that we're going to write down. It turns out that we can say a lot more about the relationship between R and S if phi happens to be surjective. We really like surjective homomorphisms. They have a lot going for us. Obviously, they're very close to being isomorphisms already. They are already homomorphisms that are surjective. They just might not be injective. But when we have a surjective homomorphism, then we can say a lot more about the relationship between the structure of R and S. Continuing our theorem, if phi is surjective, then the following additional statements hold. So number 9, if R has unity, then S has unity also, and phi of the one element in R is equal to the one element in S, where 1R is the identity of R, the multiplicative identity of R, and 1S is the multiplicative identity of S. So if phi is a surjective map and a surjective homomorphism rather, and R is a ring with unity, then not only does 0 go to 0, but 1 goes to 1. Homomorphisms have a lot of structure required. Number 10 says if A is an ideal of R, then phi of A is an ideal of S. So it doesn't necessarily hold if phi is not surjective, but it does if phi is surjective. Number 11, if R is commutative, then S is commutative. And 13, if phi is an isomorphism, then the inverse function, the set theoretic inverse function from S to R, is also an isomorphism. And then 14, if phi from R to S and psi from S to T are isomorphisms, then the composition, psi composed with phi from R to T, is an isomorphism. Okay, so that's the end of that theorem. All right, so there are a lot of pieces there. And many of them are familiar. Many of them come from statements that we have about groups, but some of them are less familiar and are based more on the particular structure we have for rings. As we work more with these facts, they're going to become more intuitive, more familiar to us. I just want to point out one immediate consequence of the things that we've done. So by an example that we had, the first example we had today, and parts 13 and 14 of the theorem, 108, we have that isomorphism of rings is an equivalence relation. We saw in the example that every ring is isomorphic to itself, so isomorphism is reflexive. 13 here says that if R is isomorphic to S, then you can just take the set theoretic inverse of one of those isomorphisms and get an isomorphism from S to R. So if R is isomorphic to S, then S is isomorphic to R. Isomorphism is symmetric. And then finally, 14 can be re-expressed as saying that if R is isomorphic to S and S is isomorphic to T, then R is isomorphic to T. In other words, isomorphism is transitive. So isomorphism of rings, just like isomorphism of groups, is an equivalence relation. Now, as we go on and we start looking to be able to build homomorphisms and work with them, prove things about them, we're going to have one lemma that's going to be very useful to us. When I went through algebra the first time, I feel like this next lemma was used occasionally but never made explicit mention of, but I think it would have really helped to do so. So that's what I'm going to do now. So lemma 109 says, let phi from R to S be a ring homomorphism and I an ideal of R such that I is a subset of the kernel of phi. So I is an ideal of R, but everything in I is in the kernel of phi, which means that everything in I gets sent to the zero element of S. In this case, the map psi going from R mod I, the factoring R mod I, to S, given by psi of x plus I equals phi of x, is a ring homomorphism. Furthermore, we have that phi is equal to the composition of psi with pi, where pi from R to R mod I is the natural projection map. So this is the map taking any element x of R to x plus I. Before launching into the proof, let's look at this a bit and see what it says. We've got this homomorphism from R to S. I'm making no other assumptions about it. It might be surjective, injective, don't know. But it's saying that if I take some ideal of R where I is a subset of the kernel of phi, then I can construct this homomorphism from R mod I to S. Intuitively, remember that constructing the factor ring R mod I is essentially taking the ring R, but turning everything that was in the ideal I into 0. We're going to treat everything that was in I as 0, collapse that down, and the new ring that we get out of that is the factor ring R mod I. Well, the point here is that if we're looking at an ideal that already lay inside the kernel of phi, then they were already going to zero. The homomorphism phi was kind of already treating all the elements of I as zero already, because it was sending them all to zero. And so we lose no information as far as the homomorphism phi is concerned by actually moving to the factor group and quotienting out by I, because the homomorphism phi was sending all of those elements to zero to begin with. So that's sort of the intuition behind what's going on here. The proof is not too difficult once we show that this function psi is well defined. Anytime we are defining a function and we're starting with a factor ring, we need to make sure that the way that we're describing it doesn't depend on the representatives of the cosets. You'll notice that we defined psi in terms of a representative. We said psi of this coset, x plus I, is phi of x. We need to make sure that if we take some other representative of this coset, that we get the same output out of it. So let's show that phi is well defined. So to do that, we want to let x plus I equal y plus I. These are elements in the factor ring R mod I. And we want to show, I'm sorry, not that phi is well defined, phi is given to us. We want to show that psi is well defined. We need to show that psi of x plus I equals psi of y plus I. So let's see, what does this mean? If x plus I equals y plus I, then that means that x minus y belongs to I. That's what it means for two cosets of I to be equal to each other. But we know that I is a subset of the kernel of phi. That was the whole point. The one condition we had on I is that it was a subset of the kernel of phi. So that means that x minus y belongs to the kernel of phi, and hence phi of x minus y equals 0. Here, this is the 0 inside the S ring. I'm going to forego the subscripts for now unless it becomes something becomes less clear. But since phi is a homomorphism, that means that phi of x minus phi of y equals 0. Because phi is a homomorphism, it respects addition, which means it respects subtraction as well. And so phi of x minus y becomes phi of x minus phi of y. And so in particular, this means that phi of x equals phi of y. So just finishing stuff up, we have that psi of x plus I is equal to phi of x. That's by definition. We just showed that because I is contained in the kernel of phi, phi of x is equal to phi of y. But phi of y is exactly psi of y plus I. So we've shown that as long as the two cosets are the same, it doesn't matter whether we take two representatives, an x and a y, as long as it's the same coset, we're going to get the same output out of the function psi. So hence psi is well defined. Now, proving that psi is a ring homomorphism is dead simple. You can find the details in the notes. Not going to go through them here. I'm just going to note phi is a ring homomorphism. And so let's just handle the last bit here. We want to show that phi is equal to psi composed with pi, where pi is this function that goes from R to R mod I. So let's let x be an element of R, then psi composed with pi of x is equal to psi of pi of x. Pi of x, by definition, is x plus I, and then psi of x plus I is given as phi of x. So we have that for any input to R, the function on the left, psi composed with pi, and the function on the right, phi, have the same output, therefore they are the same function. So hence, psi composed with pi is equal to phi. Incidentally, this can be written down, that's the end of the proof, but this last bit here can be written down in a particular diagram. This is what's known as a commutative diagram, where we've got some number of algebraic objects, in this case rings, and we're saying that we've got a function from R to S, which is phi that we started with. And what the proof says is that we can construct this homomorphism psi that goes from R mod I to S, and we've got this homomorphism pi that goes from R to R mod I, the projection one, and the diagram commutes. This symbol in the middle, this swirly arrow, says that no matter how you get from one part of the diagram to the other, tracing along these lines, meaning apply this function, then this function, you get the same thing. That if I go straight from R to S via phi, or if I apply pi and then apply psi, I get the same result. So this is an example of a commutative diagram, and there's quite a lot of work that's done in advanced algebra that involves complex diagrams with a whole bunch of different rings or groups or other algebraic structures, where you trace the paths of objects along these various arrows, and it can be quite beautiful the way that things all work together. Okay, so now that we have this, we're going to use this lemma to prove one of the most important results involving isomorphisms, and this theorem allows us to show that lots of rings are isomorphic to each other. And this is known as the First Isomorphism Theorem for rings, Theorem 110. And it's very similar to the first isomorphism theorem for groups that we encountered back last course. Now, properly speaking, historically, the first isomorphism theorem is only the second part of what I'm about to write down. I've got a little technical thing that I wanted to include here rather than including it as a separate numbered theorem. So let's let R be a ring. A set K, which is a subset of R, is an ideal if and only if it is if and only if K equals the kernel of Phi for some ring homomorphism phi from R to S. So this is the first part of the theorem. It says a result that's very similar to what we had for normal subgroups and kernels. For groups, we had that a subgroup is a normal subgroup if and only if it's the kernel of some group homomorphism. This is completely analogous. A set is an ideal if and only if it's the kernel of some ring homomorphism. So we've got that result first, and then second we have that if phi from R to S is a surjective ring homomorphism, then the factor ring R mod the kernel of phi is isomorphic to S under the isomorphism phi bar, defined by phi bar of x plus the kernel of phi equals phi of x. Instead of this phi bar, actually, I'm going to write this as psi, because this is the same psi that we constructed in Lemma 109. All right, so this says that if we've got a surjective ring homomorphism, then we can get an isomorphism out of it. We can get the isomorphism of the domain of the ring, the domain of the homomorphism mod the kernel of that homomorphism, and that's isomorphic to S, where S is our surjective ring homomorphism. Let me also mention an alternative form of this, which we will use occasionally, and sometimes it's written that way. It simply says that if phi from R to S is any ring homomorphism, then we have that R mod the kernel of phi is isomorphic to the image of phi. Using the same type of function here. So the way that this second part works, if we already know the first isomorphism theorem, then if we have any ring homomorphism, then phi, any homomorphism, is always surjective onto its image by definition. And so since we have phi from R to S, we can construct phi from R to the image of phi, which is then surjective, and then we can apply the first isomorphism theorem that we have here. So we will use either of these forms. The form that I have written that we're going to prove is a little bit, just a little bit cleaner to actually prove. Speaking of, let's go ahead and get started with that. So let's let K, subset of R, be an ideal. We're going to try to prove that it is the kernel of some ring homomorphism, phi from R to S. And just like with groups, we're going to let phi from R to R mod K. Because K is an ideal, we can form the factor group R mod K. And we can define this phi as phi of x is equal to x plus k. This phi is actually just the pi from before, just the natural projection map. So phi is easily seen to be a ring homomorphism, basically by definition. Further, we have that x is in the kernel of phi if and only if phi of x is equal to 0 plus k, which happens if and only if x plus k is equal to 0 plus k, which happens if and only if x is in k. So x is in the kernel of phi if and only if x is in k, which means that k is actually equal to the kernel of phi. So that proves one direction of the first statement of the theorem. So the other direction is even easier. So let's suppose phi from R to S is a homomorphism and let's let K be the kernel of phi by theorem 108 part 6, we have that K is equal to the kernel of phi, which is equal to the preimage of the ideal 0, and so K is an ideal. Preimages of ideals are always ideals, and so since the kernel is the preimage of the 0 ideal, it has to be an ideal itself. So kernels of homomorphisms are ideals. Okay, so that's sort of the setup here. The actual first isomorphism theorems, as you'd find stated in books, in other books, is this second part. So let's go ahead and prove that one. So now we're going to suppose that phi from R to S is a surjective ring homomorphism. And let's let K be the kernel of phi. So we have that by lemma 109, the map psi from R mod K to S given by psi of x plus k equals phi of x is well defined and a homomorphism. Because k is itself, of course, a subset of the kernel. So we can construct this map from R mod k to S. The thing that we're going to try to show now is that psi is bijective. Now, since phi is surjective and phi is equal to psi composed with pi, where pi from R to R mod k is the projection map, we must have that psi is surjective. We had this result way back in chapter 1 that if a composition of functions is surjective, then the last function to apply must be surjective. So since we know that phi is surjective and it's equal to this composition, then psi must be surjective. All right, so then we want to show that psi is injective. We're going to do that by showing that the kernel of psi is just the 0 ideal. So let's let x plus k be in the kernel of psi. So that means that 0 is equal to psi of x plus k, which is equal to phi of x. So that means that phi of x is equal to 0, which means that x is in the kernel of phi, which is k. So that means that x plus k is equal to 0 plus k. And so that means that the kernel of psi consists of only the element 0 plus k, which is the 0 element of the ring R mod k. Thus, psi is surjective. I'm sorry, injective. I showed it surjectivity already. Psi is injective by Theorem 108, part 7. Part 7 was the one that allowed us to conclude that a homomorphism is injective if its kernel is trivial. Therefore, psi is a bijection, hence an isomorphism. And thus R mod K is isomorphic to S, which is what we wanted to prove. And that finishes the first isomorphism theorem. All right, let's do a couple of examples. Let's let R be the set Z adjoin X. This is polynomials with coefficients that are integers and in the variable X. And let's let phi from R to Z be given by phi of a polynomial f equals f of 0. Which means that it's the constant term of f. So f of 0 means plug 0 in for all the x's, of course, and so f of 0 just gives the constant term of the polynomial f. Phi is a surjective ring homomorphism, and that's fairly easy to work out and see. Phi is a surjective ring homomorphism. And so that means that we can apply the first isomorphism theorem to it. And to do that properly, we want to know what the kernel of phi is. So the kernel of phi is going to be the set of all f's in R such that phi of f is equal to 0. That's going to be the set of all f in R such that f has constant term 0. Which means that every element or every term of f has degree at least 1. Well, the set of all polynomials which have no constant term is actually the ideal generated by x. We know that the kernel of phi is an ideal. We just proved that. And in fact, it's the ideal generated by the single element x in this ring. So, therefore, by the first isomorphism theorem, we have that Z adjoin X mod the ideal generated by X is isomorphic to the integers. So we've shown that this factor ring Z adjoin X mod X is isomorphic as rings to the ring Z. This lets us understand this factoring better. Now, just as a short aside, this is special for the ideal generated by X. If we did something else, if we looked at the ideal generated by X modulo the ideal generated by X squared, this is not isomorphic to Z. And the reason we could tell this is the following. In the ring Z adjoin X mod X squared, if I look at the element X, or X bar in this factoring, and multiply it by itself, then that would be the equivalence class of X squared, or the coset with representative X squared. But in this ring, X squared is 0. By quotienting out by the ideal generated by X squared, we've said that X squared is equal to 0, so we've got 0. So we just took, in this ring, two non-zero elements of the ring, multiplied them together to get 0. So this means that z adjoin x mod x squared is not a domain. So the left-hand side of this statement is not a domain, but the right-hand side is, and therefore they can't possibly be isomorphic. If two rings are isomorphic, they share all of the same algebraic properties, including whether or not they're a domain, whether they're commutative, etc., etc., etc. All right, let's look at another example which will explain at least a little bit of terminology from before. So we can show that any ring with unity, any ring containing a one element, contains as a subring an isomorphic copy of either the integers or the quotient ring z mod nz for some n. Okay, so let's see this. So let's let R be a ring with unity, and let's define a function phi from z to r by phi of a number n equals n times 1, n times the multiplicative identity. Now, of course, I'm writing it this way. N doesn't necessarily belong to R, but 1 is the multiplicative identity, and so when we write n times 1, we mean 1 plus 1 plus 1, blah, 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 plus 1 n times. And that's if n is positive. And then if n is negative, then we're adding up -1 a bunch of times. Now, phi is a ring homomorphism. Let's actually check this one. We've skipped over checking a couple of them. So phi is a ring homomorphism, which means that we want to show that if I take phi of m plus n, that I'm somehow going to get phi of m plus phi of n, where this addition happens in z and this addition happens in r. So phi of m plus n is, by definition, m plus n times 1. So this is adding up m plus n times. But if we add up 1 m plus n times, then we can certainly add it up. We can certainly break it up to have the first m summands, then the first n summands. So this is the same as m times 1 plus n times 1, which gives us phi of m times plus phi of n. Back when we defined this notation of multiplying elements by integers, we stated this relationship that the ring elements basically distribute over the integers. And similarly, if we have phi of mn, this is equal to mn times 1, which is equal to mn times 1 times 1, which is equal to m times 1 times n times 1, which is phi of m times phi of n. So this shows that phi is a ring homomorphism from Z to R. In particular, this shows that any ring with unity, there is a homomorphism from Z into any ring with unity. This shows us that phi is a ring homomorphism. Now, phi is almost certainly not surjective. Most rings have lots and lots of things about them other than the image of phi. However, remember the alternate version of the first isomorphism theorem we talked about that applies even to homomorphisms that aren't surjective. By the first isomorphism theorem, we have that Z mod the kernel of phi is isomorphic to the image of phi. And remember, the image of phi is a subset of the ring R, and furthermore, it's a subring of the ring R because it's the image of a ring under a homomorphism. Now, the last thing that we need to show is that the kernel of phi is an ideal. And all ideals of the integers are of the form n times z for some natural number n. So, if n is equal to 0, then phi is already injective, because in that case the kernel would be just the 0 ideal. So in that case, z is isomorphic to the image of phi, and in this case the ring contains an isomorphic copy of the integers. If n is greater than 0, then the image of phi is isomorphic now to z mod n z. So that means that, or let me write this the other way. In this case, we'd have that z mod n z is isomorphic to the image of phi, which is again a subring of R. So that means that R contains a subring of, or contains an isomorphic copy of z mod nz. So this proves the theorem, or the example, what we were trying to prove. But I do want to note that in any case, the number n, here is the characteristic of the ring R. And so this is sort of the justification for why we called rings where adding up one a bunch of times never got you back to 0. We called them characteristic 0, and that's because that corresponds to the case when the ring contains, actually contains an isomorphic copy of the integers. All right, that's it for now. We're going to take advantage of these facts about homomorphisms and isomorphism theorems and so forth as we move on and study more about rings and their relationships to one another. And in particular, we're going to return here when we do our study of fields.